Hi, in this video I'm going to run you through how hearing works and some information about it. So first of all, hearing is what we call a type 2 sensory system. And what's important to understand about type 2 sensory systems is that they basically have a stimulus, they have a specialized receptor cell, and then they have a neuron that they're transmitted to. Now, it's important to understand that this is connected via neurotransmitters here, but there isn't any polar cell or any sort of cell in the middle or a relay cell of any sort. So that's what the sensory system of the hearing system looks like. Now, if we look at the ear, generally we can break it into three parts. The first is the external ear. The external ear is probably what you can kind of see, I guess, from the outside, and basically everything except past the ear canal. So it basically includes the pinna, the tragus, the concha, and it's really the outer ear. If I was to draw it roughly, that outer ear, one of the main sort of purposes for this is to funnel the sound through the ear canal through to the ear drum. Here, the eardrum. So, this also has some roles. This sort of part here has some roles in the perception of the direction of sound. And we'll talk a little bit about that later. But that's really the external ear, and we'll deep dive into more in a second. The middle ear really starts with the eardrum, and it has three main bones called the ocelles, which is really about amplifying the sound. And then the inner ear is primarily made up of the cochlea. And this is basically a very hard bone encapsulated fluid, and then it's got two windows that open, and inside are all the receptor cells, and we'll talk a little bit about how that works shortly. But that's essentially the process of what it sort of looks like. So let's have a look quickly at the next stage, which is how sound goes through to the ear. So the first thing is you have sound out in the world. Sound travels through, it goes through into the external ear canal. And that's from the whole external ear canal. And that's from the hole in your the outside of your ear, and that travels through to the eardrum, and that area there is called the tympanum. And the tympanum is basically the membrane that separates the ear canal from the middle ear. Then it will move into the middle ear, which, as we know, is made up of three bones. Okay? The first, each of these bones, their job is almost like an amplification. So one hits the other, which hits the other, and that is how you get a louder and louder sound. So the first is the malleus. The second is the incus. And the third, which is the one that taps onto the windows, is called the stapes. Now the stapes is going to take all of that sound that's been amplified here and bring it into a small hole which is covered in a membrane and enters into the cochlea. And that window which it enters through is called the oval window. And it's going to come through here, and then that sound, that vibration is going to leave by the round window. We'll show all of this in a lot more detail. It's really just about setting the context about what it looks like. So I mentioned before about the external ear and the different parts and what they do. Probably the most important thing to understand about the external ear is its primary purpose is to get sound to properly enter in to the external ear canal. Okay? The secondary purpose is up here, the area called the pinna. The pinna is responsible for helping us perceive the direction of sound and if something is visible. Now, if we lose this, say, a boxer has his ear broken or this gets cut off somehow, people lose the ability to determine which direction sound is coming from. Is it coming from behind them, in front of them? It's a really important part of it right there. So then we basically want to talk a little bit about middle ear. Now, why do we have a middle ear? Couldn't we just send sound, directly from here to here? Well, the answer is that we need it to amplify the sound. If we don't amplify sound, then we have no ability to hear it, or at least hear it well, in the later part of the ear. So that is really essentially what you have all of these different parts of the ear doing. So when you enter into the middle ear, you have a few things. It goes past the eardrum, and like we said, it goes into the malleus, then the incus, and then hits the stapes and enters into the cochlea through the oval window. Now, it's really important to understand that this is driven by three main factors. The first factor is the area of the tympum, which is that small, is that sort of entryway at the eardrum, is much larger than the stapes. So what that basically means is that you have a huge amount of pressure coming in through past the eardrum, and it's being amplified into a small area here at the stapes. Now, what that basically means is that basically that sound will get more and more powerful and the vibrations will get stronger because it's being pushed from a larger to a smaller area. That's really an important point to make, which is the area of the tympanum is much bigger than the area of the stapes. Okay, so now moving down again, the next thing we really want to talk about that drives this amplification in the middle ear is that the ocelles acts like a lever. Acts like a lever. And what does that mean? Basically, if you've ever used a lever before, you know that a little bit of movement here can make a huge amount of impact across the system. And it's the same thing. When the ocelles opens up the oval window, it takes a small amount of energy and produces a large amount of energy and waves further down. The third point is that the tympanum vibrates in a complex fashion. So rather than just being sort of a flat plate like this, the way it will vibrate when pushed up against by the sound is it will sort of go in and then out and in and out, and that process in itself helps create larger vibrations for the ear to hear. But the main point, without deep diving into all of those mechanisms in too much detail, is that the middle ear is really about amplifying the sound for for the inner ear. So let's talk a little bit about the inner ear and how that impact sort of happens. So the inner ear, to understand it, we need to really understand what it looks like. So the cochlea is the inner ear, and basically the structure of the cochlea is it kind of looks like a repeated look of system that sort of looks a little bit like this, where you have the auditory nerve, and it's connected to all of these different sort of, I guess the way the ovals that look like this, which are called cochlear partitions, okay? And obviously there's, literally thousands and thousands of these. We're only drawing a few of them for the purpose. But this is our auditory nerve. And this is the cochlear partition. Well, more specifically, the cochlear partition is this part inside, and then on either side you'll have some membranes as well. So what that kind of looks like is that this here is extracellular fluid. Okay, I'm going to sort of make it a little bit lighter just to make it easy to see. These two compartments next to the cochlear partition are extracellular fluid, and they're very characteristic of the extracellular fluid. Like, they have more Na, sodium outside. They're generally negatively charged. I'm sorry, they're positively charged, etc. However, the cochlear partition here is a little bit different. It's an exceptional sort of fluid in that it has a higher amount of potassium in the fluid that is in the cell. So its extracellular fluid is more intensely more potassium rich, and in that sits the actual nerve structures, which we'll talk about there. So the nerve structure there is basically going to be sitting in a fluid that is unlike extracellular fluid here, or anywhere else in the cell, in that it's highly rich in potassium. Okay? And so when you sort of get a little bit deeper, you'll be able to look at all these nerves these lines I've drawn. And let's sort of look at this as like a magnifying glass, and it looks a little bit more like this, where you have all of these hair cells lined up. And the way they're sort of lined up is in a direction from the tallest through to the smallest, and they're lined up in that sort of direction. And that's a really important part. And that structure that's sitting in, which I call the nerves, it's sort of more specifically called the organ or corti. And this is basically a bunch of cells that are sitting on top of the membrane, and they're the hair cells in the body. And I just really want to stress the point I made before, that the fluid they're sitting on in that middle component is high in potassium and low in sodium. Okay? And basically the difference in this area, it's positive, so it's plus 90 to plus 80 as well. That's sort of the difference you'll see between normal extracellular fluid and that sort of fluid that we're talking about here. So these hair cells are called stereocilia. And they're connected through to an afferent nerve fiber. So we know that their movement is very, very important to signaling. And it turns out that process is a mechanically gated process, meaning that it's the movement itself of those hairs which determines what message is sent through to the brain. Now, what's really important to understand here is that each of these stereocilia, if I was to draw them in a bigger sort of line, they're linked by what we call a tip. Okay, so it looks a bit like this. They're not independent. They're linked by a tip. And it turns out pushing it in one direction or the other direction opens and closes different ion channels, okay? And more specifically, if I am opening the ion channels, what do you think is going to happen? Well, because it's sitting in a potassium-rich substance, the potassium is going to come flowing into the cell. Okay? So it's going to come through those hairs, the top, and it's going to travel all the way through and diffuse out into the fluid. Because remember, it's sitting in a circular sort of bath here, right? So it's going to come in the top and then diffuse to the bottom. And all of them like that are going to do sort of the same. And that's potassium entering is very different typically to what we would see in other cells where there's a lower amount of potassium in the cell, more in the cell than out of the cell. So that's just a really important exception to understand here. Now, because of this, you'll be able to see a polarization and a depolarization in the cell. When potassium flows into the cell, you're going to get a depolarization, which will help trigger the release of neurotransmitters, which will help create action potentials. Now, this process here is called a receptor potential. And just like we talked about, excitatory inputs and inhibitory postsynaptic potentials, it's really important to understand that receptor potentials pretty much share all of the characteristics of those, except that we call them receptor potentials in the sensory system. So one of the other things I didn't mention to you is that we have two kinds of hair cells. We have inner hair cells, and then we have outer hair cells. And it turns out we have only one row of these inner hair cells, but we have a bunch of outer hair cells. Three rows. So we know that it's the inner hair cells that are sending the messages to the brain. But it turns out that the outer hair cells, their job is to make something more bouncy, to sort of amplify the message to some degree, and they contain a lot of contractile proteins, and that makes the cochlea much more sensitive to low sounds. If we didn't have the outer hair cells, we would not have the ability in the cochlea to hear low sounds. So it's really important to understand that. Now, what happens, let's look at actually what happens when sound enters into the cochlea. So let's imagine, now we understand the hair cells, this is the cochlea. And I've told you guys that this is a hard, bony surface. But it has two holes. Up the top here, it has an oval window, and down the bottom here, it has a small round window. And the stapes, that little bone from the ocelles, sort of looks like this. And these windows, they're very much membranes. So they're quite thin. They have the ability to be pushed against and pushed back against, and it's not bone in those points. So what typically happens here is you have all these cells and these little partitions all throughout here. Okay, and they do go all the way to the base. I should finish them there. So they'll continue all the way through. And this whole area, I want you to imagine this is completely filled with water or fluid, okay? So it's all wet and there's lots of water in there. So when the sound enters through here, because it's been amplified, it will travel throughout here and it will vibrate and change the contents of the water and the fluid inside. So that will travel and then it will come out here again, because it can't just always stay trapped in the cochlea, and it will exit through the round window. The water doesn't, but the vibration does. The contents stay the same inside. And while it's happening here, what's happening is these cilia, these stereocilia inside the cochlear partitions, they're getting moved. They're moving backwards and forward, and they're opening and closing ion channels. And that's basically what is actually triggering the change. So what really happens here is that the sounds are going to travel through here, and the movement of the water is going to force those hairs to open and close. Because like we mentioned, if they go this way, they open, and they go that way, they close, and vice versa. So what ends up happening is it's the movement and the displacement itself of the cochlear contents, the fluid, which is the driving force of hearing. Now, interestingly, when you sort of look at this process, do you think that all of these receptors are the same? The answer is no. So what typically happens is the ones closest to the entryway or the base, the cochlear base, are going to have a high frequency, okay? And the ones further away are going to be really good at detecting low frequencies. And typically, high frequency sounds are associated with speech and the ability to be able to tell the detail of sounds. Low frequency is associated with loudness. So what happens if you get rid of the high frequency is that you may be able to hear someone speaking, but you can't exactly tell what they're saying and the detail. So this is quite commonly what happens when people start to lose hearing loss. There's some damage at this point or in to this area, and they can still hear sound, but they can't exactly hear all of the detail that makes a conversation. So, like I said before, just to recap, it is the movement of the contents that opens and closes things. In rest position, the hairs would probably look something like this. However, once they've been vibrated a certain direction, the hairs look like this. And the movement and closing of the hairs causes the polarization. If my hairs move this way and the receptor channels open, you're going to have an influx of potassium, and we're going to have depolarization of the cell. If the hairs stand like this, we're going to have closed, and it's going to be okay. But if the hairs go this way, we're going to have hyperpolarization as well. So that's why you have this ability for different directions of the hairs make the big differences in the sort of cellular response. And unlike we talked about with the eye, where it's hyperpolarization, which signals a receptor potential, in the in the hearing system, just like most systems in the body, depolarization, as in an increase in the positivity of the cell, is what triggers the sound to be graded, become a receptor potential, which can eventually become an action potential. So the next thing I want to talk a little bit about is that the transmission, the chemical transmission really mediates the sounds that come out. So it's important to understand is that once these sounds, so these different vibrations are heard, and you have a depolarization or depolarization of the cell, it is then a receptor potential that goes and creates the situation where neurotransmitters are released, and they will move across to the receptor, the receptors of the ganglion cells at the end.